Morning everybody. Welcome. Thanks for coming along. I'll introduce myself in a sec, but I just wanted to talk about what we're going to talk about, which is a lightweight root of trust, which is going to help customers enforce security in their products. Because as you know, security is becoming more and more important. Legislation is coming along, and we're trying to help that in implementing a small, easy to use, lightweight root of trust. And that's what we're going to talk about. So, my name is Chris Jones. I work for Quantique. I'm here with our partner from Siemens. This is Lee Harrison. And he's going to talk a little bit about a use case for this root of trust that we're going to detail in today's presentation. So, a little bit about Crypto Quantique. We have a stand. We're at H10. Pop round and have a look at our products. We have cloud-based products and root of trust-based products, of course. We're based in London. We've been around since 2016. And we help customers in implementing chip-to-cloud products and making sure those products are secure. So we provide silicon IP, so chip designers are part of our team. We provide embedded software to enable secure communications to cloud services. And we also have a cloud platform which can help you manage the security of your connected products throughout their lifecycle. So quite a range of products, chip to cloud, basically. So with that context, I'm sure you've heard that there's a lot about connected devices and the security issues that we have when we connect IoT products to the cloud. People hacking into your local networks, your network at home, and doing bad things. So we're in this age of connectivity. The growth is stellar. And we basically need to make sure that the data on these devices, the personal data, test data, in the case of doing tests on chips, we need to make sure that this is protected. And that's really where we're focused, ensuring that these products that are connected are protected. And we start with what we call a root of trust. So this is the key to security on a connected device. You have to have something inside that device that you can truly trust. And that's what we call the root of trust. Typically, it's embedded in the silicon of the device. There are various different ways of implementing it. And that root of trust is where everything, the security begins. That's where it starts. And you build on that as you go through the process of connecting that to a cloud service. So a little bit more detail. What is this root of trust? I'm sure some of you have heard of them. And this is a quote from the Trusted Computing Group, which is looking into this area, building microcontrollers that can be trusted. And they say a root of trust is an essential, very important, foundational security component that provides a set of trustworthy functions. And here we've got a list of those functions that are key to this root of trust and are really important. So one of them here is the unique cryptographic identity. That's an area that ourselves at Crypto Quantique are very interested in, and we've developed silicon IP that ensures that you can have a unique identity, but the important thing is that it's provable. And we can do this from a cryptographic, a quantum source, to make sure the entropy is very high. So this unique cryptographic identity is not just a number. That sometimes silicon devices, MCUs, have a unique number embedded, but it's just a number. You need to be able to prove that the device owns that number. So it has to be a provable identity. Verification, of course. So you need to be able to verify, this root of trust needs to be able to verify that the software that you're running is the correct software and hasn't been hacked or modified. In the case of roots of trust, you also sometimes need to report on the availability of the device, the security of the device. So it typically can be challenged. An external micro may request the root of trust to determine whether it's running the correct software, everything is in order, and it can provide reports to do that. Measurement, this is where it would actually look at the firmware and do a hash on that firmware to ensure that it hasn't been corrupted or hacked. And also measurement can be looking at sensors which are directly connected to that root of trust temperature sensors and other things, and do measurements on that. Secure storage, of course, is very important because your root of trust has your cryptographic keys embedded inside it, and they must be held secure. So not accessible by the outside world, not visible to any sort of side channel attack on that device, and typically well protected. And then you have trusted boot. So that's very key to security and is very much part of the new Cyber Resilience Act that is coming into play in Europe in 2027, where a device has to have some kind of trusted root or a secure boot, we call it. So this is where that device runs through an immutable process of that first boot software to ensure that it is running secure code. So it typically does a hash on it and checks it with the root of trust. So this is what typically we see inside a root of trust. And as you can see, there's some complex functions embedded in there. And there are lots of devices out there that can implement these. So these are some examples of hardware trusted solutions. So we have over here, we have some open source roots of trust. These are available, obviously, you can download them and add to them as you wish, and typically get implemented on an SoC or a microprocessor, and some of them in FPGAs. And these are quite large. They typically have a couple of cores inside them, typically a couple of RISC-V cores. They have asymmetric key generation capabilities and all the other crypto IPs needed to implement a root of trust. But they tend to be rather big, so hundreds of Ks of gates to implement these. And they're fine. They obviously are important for a lot of large SoCs. Then typically what you guys probably are more familiar with is a trusted platform module. So it's a TPM. All your laptops have got one. And this is usually a secondary chip, communicates with the main processor through an SPI or maybe I2C interface. And it is, again, the holder of your keys and can do some of these cryptographic functions, typically encryption. They can do secure boot and also measurements, attestation of your device. So that's a TPM module. Typically, you would add that to your product to be the root of trust. And then you get the dedicated secure ones, which is proprietary roots of trust. So things like Samsung's Vault. So these are the different types. But they typically, first one, very large gate count. Secondary one is a separate device, typically, and quite a large device as well. I'll go into it in a little bit more detail. And then these are huge behemoths of security processors. So they're hardware-based security, which is key, which is what we're pitching today. It's a hardware-based security. They store all the cryptographic keys, and they do all the verifications, such as secure boot, and part of secure processors and hardware accessories. So let's have a look at a little bit about TPM, a little bit to give you some idea of how this compares to our lightweight root of trust. So as I said, this is a dedicated chip, typically, that is connected to a main processor. It has cryptographic elements inside, IPs, to do encryption, key generation, and typically it can do symmetric key encryption, and it has asymmetric algorithms embedded as well, which are typically quite large to implement. They're also usually shielded, so typically they have a mesh over the top of the silicon die, so you can't actually access the silicon directly. And there's usually no part numbers on them if you decap them or anything like that. So there's an awful lot of protection on the device, and also side channel protection as well. So they're very, very secure and very popular and used in a lot of applications. They have this register called Platform Configuration Registers, a very special register in the TPM. So this is a register that you can only really write to and reset typically. And what this does, it automatically generates a hash code, or what they call a digest, from say a piece of firmware that you want to check. So you would just basically push the firmware to the TPM. It would get the data, the chunks of data coming in, and it would automatically generate a hash from that, which you cannot change. You can simply read the hash. And that's used for checking the integrity of your software. So those are the type of functions it has. And it has a spec. I think we're at TPM 2 right now. Maybe wrong there, but I didn't check. But it's a specification which you can read. And as you can see here, it has a lot of commands associated with it. So there's a lot of APIs, so up to 130 commands. So it is still quite a big, complex device. And what we're showing today is that there is a new way forward for this where you've got a constrained system. So this is where you have a system which is not such a big, expensive device, doesn't have such a big, expensive core on it, and you don't want to have the added expense of such a large root of trust. So this is where we can help. So this is what we call our lightweight root of trust. So it's based on two things. So one is the trusted computing group that I talked about earlier. They have developed this is called MARS, which stands for Measurement and Attestation Roots of Trust, it also has a NIST component to it as well, which I'll talk about in a second. So those two bits combined provide you with this lightweight root of trust. So it's very small. I'll talk about the size in a second. But it can do all these functions, such as measurement and attestation, as I've talked about. It has these configuration registers embedded inside it. And it's basically an IP block that you can add to an SoC that you may be building, or for a small connected product. It doesn't have all the functions of a big hairy TPM that I talked about earlier. So it has things like just a hash, a key derivation function, and it can do signing, which of course is very important. So you want to be able to sign that hash when you're checking the contents of the firmware that you're about to run. So it's very small. So you notice here it's got 9 commands. So that's a lot less than a standard TPM. So this is how it becomes a lightweight kind of device. So typically you'd have some sort of SoC or microcontroller, and it would have embedded in it as an IP block this lightweight root of trust. And that would connect to some kind of server. It's just a standard connected device measuring temperature or something in a building. And the server would be able to use that root of trust to verify the authenticity of this product. So drill down a little bit further. So one of the other reasons why this root of trust is what we call lightweight is because, as I mentioned before, some of the larger open source roots of trust have multiple processors inside them. In the case of Mars, it's implemented using a state machine. So that means that it's very much a dedicated device, and hence the smaller amount of commands. But it's still obviously an important root of trust. So it has standard APB interface, so you can connect it to any microcontroller real easily. It has the state machine, which is used for the commands, processing the commands. We have the configuration registers, so those are important registers that calculate the hash for you or do the measurement on your software. So that's important for secure boot and verifying that your software chain is intact and it's as high integrity. The DP, this is the derivation parent. So this is where you actually derive keys from the internal primary seed inside the device. So each Mars IP block that you ship, it would have a primary seed that could be injected during manufacturing. That would sit in some one-time programmable code. Or in the case of Mars from ourselves, we could provide you with a puff, a physically unclonable function, which would generate that seed automatically for you and create that from a quantum source. So it'd be a very high entropy primary seed. All the keys are derived then from that seed. That's part of the function of the IP block. And then you see down here, it also has this ASCON block. So this is developed by NIST. They put out a tender to create a very small block that was efficient at generating hashes and doing encryption. So that module is in there as well, meaning it's very small and can do these very important cryptographic IP functions very efficiently, low power and high speed. Very easy connection to your host control APB, as I said. Primary seed can be generated from our puff, And this is basically the implementation of our lightweight. The key here is you can see here we're less than 25K gates for this entire root of trust. If you look at something like the big open sources, you're talking 100K gates just for one of the cores. So it's significantly smaller than the open source IPs. And this also is including side channel attack protection as well. So it's a very intense root of trust that is being implemented in a very small area. So specifically for resource constrained devices, so very small, low cost devices, key metrics of hardware footprint and performance. So that's what we're after, very small and high performance. So we have some use case examples here. So where is this used? And here I'm going to hand over to Lee because he's going to talk to you a little bit about silicon lifecycle management and how we can implement Mars in an SoC using their products. Thanks, Lee.
Okay. Yeah, so thanks, Chris. If you could knock on to the next slide.
We can.
So just a very quick introduction to myself. So Lee Harrison, actually part of Siemens EDA. And within Siemens EDA, I'm part of what we call the Tessent team. So I'm kind of guessing probably very few people, if any, in this room know that particular group, group of products. But what I can guarantee is pretty much most of you are sat with something in your pocket that has got our IP in and was tested using our technology. So really our technology is focused on semiconductor test. So testing semiconductors at the manufacturing stage to make sure they're defect free. So when they go into the products, you don't have any problems or any weird behavior in your phone or your laptop or whatever. Now that technology, we've been developing that for over 30 years. So that technology is extremely well established in the industry. It's used pretty much everywhere. However, what we've seen, if you click again, there's some, brilliant. So what we've seen over the last few years is a bit of a shift in the industry. So DFT or test was very much focused on, we test the device, it works, that's great, we give it to the customer, and that was the end of the story. Now what we're seeing is there's this requirement and a need growing from all of the end users of semiconductors to really understand what's happening in that silicon throughout its life cycle. So no longer are people satisfied with, okay, the silicon works, that's great, no longer our problem. We want to make sure the silicon is continuing to work correctly. We look at the reliability, we look at the performance of the system. And to do that, we've grown our footprint of our technology quite significantly, adding more and more IP. And here you can see we've got everything from the manufacturing test, which is now becoming in-system test. We've got functional monitoring to look at overall functional performance and behavior. We've got structural monitors, and we've got parametric monitors. So really looking at the health of the silicon throughout its whole lifetime. Now, all of this technology creates a huge amount of data. Now, and that data, whereas in the past it would be constrained within the manufacturing facility in a nice, safe factory, it's now being pulled out of that device in the field. So it could be anywhere where that device is being used, in a garage, in a car service center. So it's really important, given the sensitivity of some of that data, that we make sure that is secure. So that's why there's an increasing need now to include security as part of our overall DFT solution. And if you click to the next. So for example, if we take automotive, and this is just one of many examples, we see now that semiconductors within your car include a whole range of technologies that you're not even aware of being there. But what they're doing is they're making sure that that piece of silicon is being constantly tested. They're making sure that from a functional safety perspective, anything that happens to that silicon whilst you're driving that car is very quickly identified, and actions are taken. We've got performance monitoring, and all of that information gets processed both on chip in the car, but it's also brought out onto the cloud. And that's where we need a level of security to make sure that all of that data is pulled out of the car in a safe and secure way, because there is quite a bit of sensitive information there. And also remember, this is a two-way street. So we're pulling data out of the car, but as you're all familiar with cars today, we're also doing over-the-air updates. So at some point, there's going to be a new software release or new software uploaded to your car, and some of that will be configuration data for the IP that you see there. So again, we need to make sure that that's all safe and secure. So in terms of how that's impacting the Siemens technology, here we have what we call our secure safety island. So most automotive semiconductors will have a safety island portion of the silicon, which is designed to essentially manage all of the safety management components within that silicon. But also now we're adding to that the security management as well. So that's where our partnership with Quantique comes in, because having a small compact root of trust is critical to this DFT environment, because this is additional logic that customers are adding to their design. It's not part of the functional design, so they see it as extra cost, extra overhead. So to minimize that footprint, the Mars root of trust is a perfect fit for what we're trying to do here. So, so in this kind of use case, what we have is we need to have access to all of the technology that we're putting on chip, but given the use case, it could be a different level of access. So here are just kind of three examples where the far one there is access to the data on the chip, which you may have access to that via an app on your phone. So it's kind of third-party app access. So a low level of access, and that data that's there. The test site could be in a vehicle garage maintenance center. So more data can be pulled out to diagnose what the problems are. And then obviously when there is a failure, and that has to go back to the actual supplier, those suppliers are required through the automotive standards to be able to root cause any failure that occurs on the silicon. So for that, they will need complete unlimited access to every diagnosis capability on the silicon. So you can have, depending on who you are, different levels of granularity in the secure access. And again, that's something that a root of trust like Mars can enable us, because you can have different keys for different people, and you can have that granularity built into the overall system. So that's just a very quick example of the use case that Siemens has for this technology. It's very compact, fits very neatly with our overall test solution, and we look forward to getting this integrated into our overall platform.
Great, thanks, Lee. Another use case I have here is where you have a remote device, and you can see here it's we're using a CAN bus example here. So you have multiple sensors on a device, or it can be in a factory as well. Something you could be like lots of sensors in a factory, all sorts of similar applications with a remote chip. And in this case, we want to make sure that that remote chip is functioning correctly, that we can talk to it, and we can verify that it's operating correctly. So this is quite common. So here we have a central processing unit on the device, which is got a Mars integrated in it, possibly one of our QDID puff IPs that are generating the seeds for the keys. And this is a very constrained device in this use case. So it's quite small, and we want to make sure that it's secure. So it's important to be able to attest this device to make sure that it is functioning correctly, running the correct software, and that it's not been hacked in any way or somebody's injected some bad software in it. So in this case, we can receive data and make sure that the device hasn't been compromised, so we can challenge it, check that it's verify that its identity is correct, and this is usually through a challenge from the main CPU. So because we're running out of time, so let me just show you the actual communication that's typically ongoing with this kind of device. So here you have the remote sensor itself, which has a microprocessor, a very small microprocessor on it, and it's talking to the outside world, to the central module through some kind of bus. So typically, as I said, it's important with the root of trust to have a secure boot mechanism. So that device is actually booting through an immutable process. And using the lightweight Mars, you can see here that the sensor microcontroller will boot up, and it will, because that first boot process is immutable and typically in ROM, it will send the next bootloader image, so the data, to the actual Mars IP block, and it will create this digest or a hash of it, and it will report the digest back. And then the microprocessor will then typically take that digest and request the Mars device to add it to the configuration register. So it will add it to it. And then as it goes through each bit of software, so the bootloader itself, and then maybe the actual executable firmware, it will do the same process. So keep adding to this digest. And eventually that digest will just be a great big hash showing the sequence of events that microprocessor has gone through to boot up and start running its code. And then the external module can then actually check that it's actually running the correct code by doing this challenge. So it will generate what we call a nonce, or a random number. It will send the command to the main processor to say, I want you to prove that you're actually running the correct software. That will be passed over to the Mars, which will take the final hash value and actually sign it with its signing key, and then send that back. So it's now proven that it actually is the correct identity that is generated that digest, and then the central CPU can take that digest and compare it with a correct version and verify that this device is actually running the correct software. So this is the kind of typical sort of function that this very lightweight module will be able to do. And as I said, it's all done in 25 gig gate, so it's extremely efficient, very small. So that's another typical use case. So if you want to learn a little bit more about this lightweight root of trust, a little bit about security, and also our other products, our security platform, please come along to H10. This is where we are with the big purple booth just up from the stage. You can't miss us. We've also got a demo running of the Mars IP, so you can actually see it running and working, and we can show you some other demos of our platform as well. So thanks very much for listening. I hope you enjoyed that, and hopefully see you later. Thanks.